Hello, today we're going to be talking about logarithms, but before we get started, why don't you start with a problem of the day? I want you to hit pause, take 3 minutes to practice for perhaps your next quiz, your next test. Total of $5,000 is invested at an annual interest rate of 3.5%. Find the balance after 7 years if it is compounded. This uses the compound interest formula and the PERT formula from yesterday. Dig those out. You will definitely want to get those in your head. You'll need to know them for your test. Hit pause 3 minutes. Okay, welcome back. You should have used these two formulas. Your quarterly indicated that it was compounded 4 times a year. Remember, your interest rate is entered as a decimal, so 0.035. So for my first value, I had $6,381 and some change. Continuously means it's an infinite number of years. So you're thinking to yourself, man, I am going to earn a lot of interest if it's compounded continuously. No, not really. Compounded continuously just maximizes the amount of interest possible, as if the number of times a year could be infinity. It's basically the asymptote for the compound interest formula. So we end up ultimately with a value of, if I can get it to come up here, there we go, $6,388.11. All right. Today we're going to be talking about logarithms. We're going to focus on bases other than base E. Tomorrow when we do some follow-up, we'll bring in E and we'll talk more about the graphing. We're also going to be doing graphing of some basics, so we're going to tie into what we did with exponential functions. I want you to take a moment to do just a quick exploration. Try to get in your head what a logarithm actually does. We're going to go to the most basic type of log on your calculator, and that's the log button, not the natural log button. The log button's found on the left-hand column of your calculator. I want you to hit pause for a minute. I want you to enter in these values, log of 100, log of 0.1, etc. Your goal before you hit play is to write down on your paper, what is the log button's function? What's it actually finding? If I type in log of 2, what is that actually calculating? So that's your goal. See what you can come up with. If you know it from last year, great. If you don't, this is a great investigation for everybody. Don't give it away. Let everybody have a chance to try. Hit pause for 1 minute. See what you can come up with. So if you entered into your calculator, you should have found log of 100 is 2. Log of 0.1 is -1. And you may have come up with this on your own at this point. You may not have. Log of 1,000 you'd find is 3. Log of 10 is 10. So maybe so far you didn't get the idea. And then I notice I have parentheses that are smaller there. Log of 10 to the 4th, you came up with 4. Now that makes you think, that's interesting. Log of 10 to the -2nd gives you -2. So it makes me think that the log is finding a power, that -2 and 4. Well, it just so happens that log of 10 is 1, the power of 10 is 1. And that actually found that to be 1, not 10. I don't know why I wrote 10. Log of 1,000, well, 1,000 is 10 cubed, so it's giving you 3. 100 is 10 squared, and it's giving you 2. You'll notice right above the log button, it says 10 to the x. So log is known as a common log. Because we're the base 10, we use the base 10 number system, tens, hundreds, thousands, 10,000s, etc. We have a common log button. It's the most common. We work with powers of 10, metric system. It's all over the place, powers of 10. So we have 10 to the x is the most prevalent. Okay, so you're thinking, why is log of 0.1? Well, 0.1 as a fraction is 1/10, which is 1 over 10 to the first. If I move that to the top, that becomes 10 to the negative first, which we come up with an answer of -1. So now type log of 2 on your calculator. Okay, if I type log of 2, I get a decimal. So now take that decimal and take 10 to that decimal. Do you get about 2? You should. Check it. Take a second to see. You can also type in log of 2 and then type 10 to the power of, and then do the answer button, which is right down at the bottom. Answer, sir, which is right at the bottom of your screen. And you can enter in the exact value, and it should give you exactly 2. See what you find out. So basically what you should have found out in this process is that a log, the log button, is finding powers of 2. So the function of a log is to find powers or exponents. So essentially, guys, when I think of logs, I say logs are exponents. It's that simple. They are interchangeable. If you want to find an exponent, you use a log. So if I take my original log of 100 and I say it's equal to 2, log of 100 is understood to have a little number right down here called base 10. Okay, you're going to see log base 2 with a little 2 down there, log base 3 with a little 3. That's our base right there. If I want to rewrite this in something that I understand that uses the 10, the 2, and the 100, I can rewrite that in an exponential form that's equivalent, that's 10 to the second equals 100. So when I look at this log base 10 of 100, I can think of what I like to refer to as the magic loop. 10 to the power of 2, go across the equal sign to get your power equals 100. So if I make that generic, log base b of some x equals y, I can say b to the y equals x. Those are equivalent. So this is called log form, logarithmic form. This is called exponential form. And depending on what you're doing, if you're trying to find an exponent, it's good to change into logs. If you're trying to find the value of a log, it's good to change into exponents. So it's like a translation factor. So to formalize that, let's go and give me just a second to clear my screen. To formalize that, we can say that log base a of some y is true if and only if a to the y equals x. So the function given by f of x equals log base a of x is called the log function with base a. It looks similar to what we talked about yesterday. Remember, we had yesterday y equal a to the x. That was an exponential function. So here, the log function can be rewritten as a to the y equal x. So notice that x and y are swapped. So therefore, a log function is the inverse of an exponential function. The log function is the inverse of an exponential function. Take a moment to write that down. The log function is the inverse of an exponential function. So we're going to use this to help us actually solve equations. Initially, you're not going to be as comfortable with a log equation. So when I see log base 2 of 16 equal y, notice it's base 2, not base 10. What I'm thinking is 2 to what power is 16? That's really what I'm trying to find. So an equivalent exponential function, if I take my little magic loop, is 2 to the y equals 16. Well, 16 can be rewritten as 2 to the 4th power. So there's what's called the one-to-one property. One-to-one property says that basically if I have 2 to the something equal to the somethings have to be equal to each other. So therefore, y has to be 4. So log base 2 of 1/2 equals y. So I'm saying 2 to what power is 1/2? So I'm going to rewrite this using my magic loop. 2 to the y equals 1/2. I'm going to think, since I have 2 to the y, I'm going to think of 1/2 as 2 to some power. So right now I have a 1 on the 2 the first on the bottom. I'm going to move it to the top, and I'm going to make that 2 to the negative first. So therefore I have 2 to the y equals 2 to the negative first. So therefore, one-to-one property says that y would be -1. So in other words, log base 2 of 1/2, if I had that button on my calculator, it would give me -1 as a result. So 2 to the -1 is 1/2. Log base 4 of 16. You try this one. Rewrite as an exponential function. You should have found 4 to the y equals 16 by doing the magic loop, as I like to call it. Rewriting 16 as a power of 4, you should be able to find 4 to what power is 16? You would find it to be 2. So log base 4 of 16 is saying 4 to what power is 16? It's 2, 4 to the second. And finally, log base 5 of 1 equal y. Try this one. Rewriting an exponential form. And then I'm thinking of 1 as 5 to the 0 power. So I can say 5 to what power is 1? Well, it's 0. All right. So logs are exponents. They are used to find exponents. Common log function. We talked about this briefly at the beginning, and you've actually done a little practice with this. We're going to talk about some of the detail. Base 10 function. If you see it just log of x, these are equivalent to each other. It's understood. There's a little 10 right down there. That's the common log. Log key on your calculator is used for that. It's used most often because of our base 10 power system, our base 10 number system. So, calculating some values on your calculator. Grab your calculator, just practice a little bit. Log of 100, we did this one already. You'd enter that in as simply log of 100. You're thinking 10 to what power is 100, so it should give you a value of 2. Log base 10 of 2/5. So when you type that in, it's saying 10 to what power is 2/5. See what it gives you? You should get -0.3979400. Now let's just kind of think this through. If I thought of this as y, it's saying 10 to what power is 2/5. 10 to what power is 2/5? Well, to give you a perspective of this, 10 to the 0 power is 1. It's less than that, so it's got to be a negative. That's why we come into that. Negative exponents are also often going to yield your values smaller than 1. Okay? Next one, log base 10 of 5. Find that on the calculator. You enter it like so. It gives you that. Take 10 to that power. See if you get 5 back out. You should get approximately that if you don't enter it in completely. And last but not least, log base 10 of -4. In other words, common log of -4. You're going to enter this on your calculator. What's it give? Should give an error. Here's why. This is saying 10 to what power is -4? Well, 10 to the 0 is 1. We can't come up with 10 to a value to get a negative number. So there's given us a domain restriction. Okay, and you can hear my dog in the background. That's Marge, the junkyard dog. Some properties that are helpful to know. I'll be honest with you, I don't use them a lot myself. I tend to overthink things. Some properties that are often used. Log base A of 1 equals 0. The reason is because we can think a to the 0 power is 1. Excuse me. So log base 5 of 1 is 0. Log base 10 of 1 is 0. Log base 100 of 1 is 0. All of those. Log base pi of 1 is 0. Log base A of A is 1, so log base pi of pi is 1 because pi to the 1 power is pi. Log base A of A to the x. So normally this is log base A of x. So basically we've replaced the x with A to the x. So we've essentially replaced the x with its inverse. We're doing a composition of functions. So essentially log base A and the A to the value cancel each other and leave the x. So composition of functions, remember if you do f of f inverse of something of x, you end up with x back out. Similarly, a to the log base A of x is equal to x. So this is called the inverse property. Helpful when you're trying to actually solve equations. And then this one's one of my favorites. It's kind of what I call the obvious property. If log of something equals log of something else, then the somethings have to be equal to each other. It's called the one-to-one property. They match up one place to one place. Okay, solving. So if I ask you to find the value of this, I could say log base 6 of 6 equals what? I could use a property. I could also think 6 to what power is 6. And that's, excuse me, going to be a value of 1. And that's one of the property 2 from earlier. So if I ask you to find log base 3 of 3 to the 5th, the 3 and the log base 3 essentially undo each other and leave the 5 as your answer. Those are nice to notice. And then log base 7, or excuse me, 7 to the power of log base 7 of x. Similarly, those essentially undo each other and leave the 9. Property 3. And then finally, graphing. Logs, remember I said, were inverses of exponential. And so that means when you swap x and y, their graphs reflect across the y equal x line, going back to chapter 1. So when we're graphing these today, I'm going to ask that you pick 5 x values. You're going to plug into the exponential function instead to find the y value, and then you're going to switch them to graph the log function. So to give you an example, and for some reason there's this floating 1, 0, you'll see it come up later. Ignore it for now. So if I have log base 2 of x and ask you to graph, your calculator generally doesn't do this very easily. It does log base e natural log, and it does log base 10, the common log, but it doesn't like to do log base 2 without a little extra work. So I'm going to instead graph its inverse, 2 to the x. So I'm going to fill in 5 values. Negative 2 to 2. 2 to the negative second is 1 over, excuse me, 2 to the positive second, which is 1/4. 2 to the negative first is 1 over 2 to the positive first, which is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. I'm going to plot those points. I'm going to draw the y equal x line, and then essentially I'm going to swap all those x and y values. I'm going to reflect them across the axis of y equal x, and I have log base 2 of x. Notice, excuse me, we had a horizontal asymptote at y equals 0 when we were graphing 2 to the x. We now have a vertical asymptote at x equals 0 for our vertical asymptote. We went through the order pair 0, 1 when we were graphing exponential functions. Now we go through the order pair 1, 0 when we graph log functions. Those are going to be key points when we're graphing each of these two types of equations. Okay, so, and then we have an x-intercept as I just mentioned. Your assignment's going to be on page 199, 7 through 43 odd, and then 109. The odds are there so you can check as you go. Don't just copy them down. That's not the point. It's to get practice with these basic skills fundamentals. Tomorrow when we come in, we'll see what kind of questions you have, and we'll pick up from there. Hope you have a great day.